All right, in this video, we're going to take a look at an application of parabolas. First up, if we take a parabola and rotate it around its axis of symmetry, which is going to split the parabola in half, we obtain a 3D model of a parabola called a paraboloid or a paraboloid of revolution. So, for instance, satellite dishes, the inside of a flashlight with the reflective surface are paraboloids or paraboloids of revolution. And the nature of them are going to allow signals to be sent either to or from the focus in a directed manner. So, for instance, when you turn on a flashlight, like a mag light or something to that effect, the light is the source. All the light is going to scatter towards the surface, that reflective surface inside, and all then, no matter where it hits, all of them are going to be focused in the same line. So they're going to be parallel. All those rays of light are going to be parallel, which allows you to see whatever it is you're shining the light on. Satellite dishes will receive the signal from outer space. The signal will bounce off the satellite dish itself and all focus on the receiver, which is a focus point for that. So, speaking of satellite dishes, that's the example we're going to use. So, a satellite dish is to be constructed in the shape of a paraboloid of revolution. So, if the receiver is going to be placed 2 feet above the vertex, where again the receiver is the focus point of a satellite dish, and the entire dish is to be 12 feet wide. So it's one of those old fashioned satellite dishes they used to have way back in the day. How deep will the satellite dish actually be? So, one of the benefits from or for working with applications of conic sections is we tend to try to get the vertex involved if possible. So with these example problems with parabolas or paraboloids, putting the vertex at the origin is going to be very helpful. And then from there, you can have the graph open whatever way you want. So I'll just have it opening up since, most satellite dishes are going up anyway. But truth be told, we could have it opening down, we could have an opening to the right, to the left, we could have the vertex be way over here, but it does make it easier to have a vertex at the origin. And here's our focus point 2 feet above the vertex, and we want to know if we have a 12-foot wide satellite dish, how far from the base will that satellite dish be? So here, if we have a vertex at the origin, opening upwards, we have x minus 0 in parentheses squared, which is just going to simplify to x squared. The value of p is 2, so 4 times p is 8 times y minus 0, or just 8y. So again, having the vertex at the origin will make the equation a lot easier to work with. So our equation of our parabola is x squared equals 8y. And if the whole thing's 12 feet, your y-axis is your axis of symmetry here, that means it's going to split your parabola into two equal parts, a left part, left half, and a right half. So if the whole thing is 12 feet, that means each half is 6 feet. So if we have x squared equals 8y, we know that the point 6y is going to be on our parabola, where again we have 6 feet going out, and now we're going to calculate what the value of y is based on x equaling 6 in this equation. So when we do that, we get 6 squared equals 8y. 6 squared is 36, so divide both sides by 8, and 36 eighths reduces to 9 halves, or 4.5. So for a 12-foot wide satellite dish, where the receiver is 2 feet away from the vertex, if the satellite dish is 12 feet wide, it's going to be 4.5 feet high or 4.5 feet tall for those conditions. All right, that about does it for this video, and I'll see you next time.